First of all, why we need multi-level inverter? If you take the normal inverter, this is the circuit diagram of this normal inverter. Here, when the MOSFET 1 and MOSFET 2 is turned on, then we are getting the positive 100. Why? Because here we are giving the positive 100 volts, then we are getting the positive 100 volts like this. Okay. When you turn on switch 3 and switch 4, you can get the negative 100, right? Like this. And then again 1 and 2, you can get the positive 100. This is the output waveform of normal inverter. Actually, the name inverter means it can convert DC to AC, right? But at the output of normal inverter, we are not getting the pure AC. We are getting the pulsating AC, that is nearer to AC, right? So if you draw the normal exact sine wave, that will be like this. Okay. The only thing is here actual AC is getting their peak value slowly. From 0, it is getting their peak value slowly, right? But in normal inverter, it is goes suddenly. It can suddenly increase the value to its peak, and it is suddenly decrease the value to its minimum. Okay. But in actual sine wave, we are getting the peak value slowly, and we are getting the its minimum value slowly. Okay. That is the problem with normal inverter. If you take the multi-level inverter, in normal inverter, we are getting the only two levels, either positive 100 or negative 100, either plus VC or minus VC. Okay. But if you take the multi-level inverter, here you can get the 3 or more levels. Like if you take the 100 volts, you can get the positive 50 and positive 100, and we can get the minus 50 and minus 100 and also 0. This is the normal 5 level inverter. Okay. If you take the exact output of 5 level inverter, then that will be like this. First of all, you can get the 50 volts, and then you can get the 100, and then 50, and then you can get the 100. Again it is 0, and then you can get 50, and then minus 100, minus 50, 0, 50, 100, 50, 0. So this is the output voltage of 5 level inverter. If you compare these two, here in normal inverter, it reaches its peak value suddenly, but in multi-level inverter, in 5 level inverter, it can reach its peak value slowly. First of all, it goes to 50, and then again 100, and it reaches its minimum value also slowly, and it can goes to 50 and then 0 and then minus 50 and minus 100. This much time it will take. So the quality of the sinusoidal output will be increased when compared to normal inverter. Here it can suddenly reaches its maximum, and it can suddenly reaches its minimum. Okay. But in multi-level inverter, it can reach its maximum value and minimum value very slowly, like what we are having in the alternative current. So this is the much nearer to pure AC when compared to normal inverter. So this is the normal 5 level inverter. If you further increase the levels of the inverter, then you can get the exact AC like this. If you further increase the inverter, like if you take 22 or 33 level, then your output will be like this, right? Okay. So when compared to normal waveform, this is much nearer to AC, right? So that is the need of multi-level inverter. Here if you increase the voltage levels, then you can get the more quality of AC waveform. And also if you increase the levels, you can also decrease the total harmonic distortion percentage of output waveform. So here when compared to these three waveforms, this is nearer to AC, right? So it has the low THD. Okay. And this is not much closer to AC. So it has more THD value. Okay. In 5 level inverter also we have the low THD when compared to this normal inverter, and this is much higher when compared to this waveform. Now let's see how multi-level inverter is. So this is the 5 level cascaded H-bridge multi-level inverter. The circuit diagram of multi-level inverter is not much tougher. It is very easy. Actually, if you take the normal inverter, that is the only 3 level inverter. Why 3 level? If you turn on S1 and S4, you can get the positive 50. If you take the 50 volts, you can get the only positive 50. If you turn on S3 and S2, you can get the negative 50, right? And if you turn on S1 and S2, you can get the 0. So this is the 3 levels only we are getting in normal inverter. Okay. If you want to increase the level of the inverter, then you need to connect the another inverter in series with the first one. That's it. Here these two are connected in series. Okay, that's why this name indicate cascaded. Cascaded means series. Cascaded H bridge multi-level inverter. So if you connect two inverters, then that is the 5 level inverter. If you take only one inverter, that is the 3 level inverter. If you take the another inverter here, then that is the 7 level inverter. If you take another, that is the 9 level. And if you take the another, then that is the 11 level inverter. So like this you can get the more levels in cascaded H bridge multi-level inverter. First we need to see the 5 level inverter, right? So here in 5 level inverter, we need to get the 4 levels, right? For example, if you take the 50 volts as this one, here we are getting the plus 50 volts when you turn on the S1 and S4, okay? And we are getting the positive 100 volts when we need to turn on the S1, S4 again, S1 dash and S4 dash, and again you get the positive 50 when you turn on S1 dash and S4 dash only, okay? And you are getting the 0 volts when you are turn on S1 and S2, S1 dash, S2 dash, because these two are short circuited. Here you get the 0 volts and here you will get the 0 volts. Then finally you can get the only 0 volts. And we are getting the minus 50 volts when we turn on the S3 and S2 only. Okay. And you can again get the minus 100 volts when you turn on S3 and S2 as well as S3 dash and S2 dash. That is the switching combinations of normal 5 level inverter. Here I am again and again telling you, I need to turn on S1 and S4, S3 and S2. So how we can turn on these switches? Here I am using only bidirectional switches. Okay, bidirectional means fully controlled switches. Okay, fully controlled switches. Here I am using the IGBT, right? You can also use MOSFET also. Okay. So here in MOSFET and IGBTs, we need to give the gate pulses, right? So how we are giving the gate pulses? By using pulse width modulation technique. Okay, let me explain about pulse width modulation. Then you can easily design our circuit in MATLAB. So this is the normal sinusoidal pulse width modulation what we have. Here we have two waves. One is reference wave, that is nothing but the sine wave. Okay, here in sinusoidal pulse width modulation, always sine wave as reference wave. Okay, and then this triangular wave as carrier wave. Okay, here we are giving the conditions. Whenever the reference wave is greater than the carrier wave, then we need to turn on the switches S1 and S2. Whenever the reference wave is less than the carrier wave, then we need to turn on the switches S3 and S4. Okay, here in this condition you can see this sine wave, nothing but the reference wave, is greater than the carrier wave, right? Then we need to turn on the switches. That's why I am giving the on condition here. Here also we are getting the reference wave is greater than the carrier wave. Then again here also we are turn on the S1 and S2. And here also we are getting the more reference wave and compared to carrier wave. Here also we can turn on. So at these conditions only switches S1 and S2 is turned on. So at this condition we need to turn on the S3 and S4. Okay, here we don't need to turn on all switches at the same time. Why? Because here if you turn on the all switches at a time, then you can get the short circuit. Okay, that's why we never turn on the all switches at a time. Okay, here we are taking only 4 switches, right? But what about below H bridge? Here we are taking the only this carrier wave and reference wave to turn on and to turn off the only 4 switches. Then what about this below figure, this below H bridge? For that purpose we need to modify this pulse width modulation. Okay, that's why I am taking the level shift pulse width modulation. Level shift pulse width modulation is just like normal pulse width modulation. Here we are taking the single sinusoidal waveform. Here I am taking the only same sine wave, but I am taking the carrier waves as 2. So that is like this. This is the level shift pulse width modulation. Here this is the reference wave. These are the 2 carrier waves. Okay, these are the carrier wave 1 and carrier wave 2. When compared this reference wave and this carrier wave, we need to turn on the S1, S2 and S3, S4 like first pulse width modulation. And if you take the reference value and this carrier wave 2, you can again turn on the S1 dash and S2 dash and S3 dash and S4 dash. That's why I am taking the 2 carrier waves. Okay, this is for 5 level inverter. Okay, here the time is same as the normal pulse width modulation 0 to 1, but the output value, this is the output value, is difference. The amplitude of the sine wave is 0 to 2. Okay, but amplitude of these carrier waves are different. For this red color carrier wave, the amplitude is 0 to 1, and this blue color carrier wave amplitude is 1 to 2. Okay, these are the output values, but time value is same, 0 to 1 for all three waves. This pulse width modulation is for 5 level, right? But if you take the 7 level inverter, what will happen? I need to again connect the another H bridge. So I need to again give the pulses to another 4 switches, right? S1 double dash and S2 double dash, S3 double dash and S4 double dash. Here I need to turn on the another H bridge switches. So here I am getting the another carrier wave. That's it. Here time value is same, 0 to 1, but amplitude is changing. Here if you take this is 1, then 0 to 1 this one, then 1 to 2 this one, and 2 to 3 this one. Okay, here sine wave amplitude is 3. Okay, if you take the again 9 level, what will happen? We need to give another 4 switches. So that is S1 triple dash, S2 triple dash, S3 triple dash, S4 triple dash, like this. Here I need to give another carrier wave. So like this, the pulse width modulation level shift pulse width modulation is changing. Okay, here amplitude is 4, 0 to 1, 1 to 2, 2 to 3, 3 to 4, but the sine wave amplitude is same. Okay, these are the things you can mind it for multi-level inverter. Okay, now let's open the MATLAB. Now open your MATLAB. After open, go to Simulink library and take elements what we need for designing. So this is the library. Take elements what we need. What we need? First of all, we need a DC source. Okay, we need a DC source and we need a IGBTs. You can take also IGBTs or MOSFETs, what you want. Okay, because the two are bidirectional switches, right? So take DC source. In simple systems, I am getting the DC source here. Okay, so take this DC source, and then what we need? We need a power electronics switches, right? So go to power electronics. You can take IGBT or MOSFETs, whatever you want. Here I am taking the MOSFET. Okay, and we connect these 4 MOSFETs to load, right? So that's why you can take the resistance load also. Okay, go to elements and take resistance load. Here you can get the RLC series load, take that one. Okay, and then what we need? We need a pulses, right? Switching pulses. How can we give switching pulses? By using pulse width modulation. This is the pulse width modulation, right? Here what we need? We need a one reference wave and one carrier wave. Reference wave is what? We need to take a sine wave, right? So go to sources. At the top you can get the sources. Here you can get the sine wave. So take the sine wave, and then what we need? We need a carrier wave, right? Carrier wave is nothing but the like triangle wave. So here you can take the repeating sequence. This is like triangle wave. So take this one. So this is the reference wave and this is the carrier wave. After that what we need? We need a, and again we need to take the less than greater than conditions, right? Because to compare reference and carrier waves. So take the relation operator. In logic and bit operators you can get the relational operator. This is the relational operator you can get in the logic and bit operators. Okay, so we add this one, and then what we need? We need a, and then what we need? We need a one NOT gate, or you can use also gain as -1. Why we need to use NOT gate means here we need to turn on S1 and S4 only. No need to turn on S1 and S4, S3 and S2 at a time. Here S1 and S4 is on. You must turn off the S3 and S4. For that purpose, you can take the NOT gate, and you can also take the gain and give it as a -1, because that two operations is same. So here I am taking the gain. I am taking the gain value is -1. You can also use, instead of gain, you can also use NOT gate also. Okay, I will tell you later why I am taking the gain as -1. Okay, and then what we need? We need a voltage measurement, right? To measure the voltage of the load. Okay, so go to measurements. You can get the voltage measurement. Okay, to measure the voltage we need a scope, right? So go to sinks. You can get the scope. And must and should what we need? We need a power GI. Without that one we can't run the circuit. Take the graphical user interface also. Okay, that's it. These are the elements what we want. Okay, now let's connect our circuit as per our circuit diagram like this. Okay, so first of all take the switches and rotate this one. Use the command Control R to rotate. Okay, so copy by right click. Okay, so take 4 switches and connect. Okay, and take another bridge also. So because we need to take 5 level, right? So that's why I'm taking the two bridges. So take two bridges and connect and give input DC sources for those two. Okay, like this, and connect it to the load. Okay, you can also rotate this one by using controller and take only resistance load. Okay, you need to zero the inductor value and capacitor value. Okay, that's it, and connect like this. Okay, connect like cascade. Okay, nothing but the connect like the series connection. Okay, measure the output voltage like what we connect in voltmeter in laboratory. Here also I am taking the voltage measurement in parallel to the load. Okay, to measure the voltage and give it to the scope to see the waveforms. That's it. Now you can take power GUI as discrete because our circuit in the discrete mode. Double click power GUI and you can get the discrete mode. Okay, that's it. And now the task is connecting the pulse width modulation. Okay, these are the level shift pulse width modulation. First of all, take reference wave and take carrier wave, right? So here also take reference wave and then take carrier wave. These two are the waves and give it to the relation operator. Okay, here the thing is giving the values to this sine wave. Here amplitude is 1, but so this is the 5 level inverter pulse width modulation, right? Here the amplitude of the sine wave is what? 0 to 2. Time is 0 to 1. So here 0 to 2, amplitude is 2, right? That's why take the sine wave amplitude is 2 and frequency is what? We know the frequency is 2 pi f. So take the 2 into pi into f as frequency 50. Okay, then click on OK button. Okay, now repeating sequence. What is the repeating sequence? Here the time values and the output values we have. What is the time value? In our waveform time value is 0 to 1, right? So this is the time value. So take the time value is 0 to 1. This is not change at all. Okay, but what is the output value? For this bridge, first H bridge, we need to take the 0 to 1, right? Then second H bridge we need to take the 1 to 2. So that's why take the repeating sequence as 0 to 1 for first H bridge. That's it, and giving to the comparator relation operator. Okay, so to turn on the S1, to turn on the S2, because we need to turn on these two switches at a time. That's why I'm taking the same pulse. Okay, so here when we need to turn on the S1, these two switches, when we turn off these two, then only we need to turn on these two, right? So here these two and these two switches are totally opposite. That's why I'm taking the gain and giving to the sine wave. I'm taking the same carrier wave and give it to the same relation operator. Here you can also take the less than condition. Okay, here I am taking the greater than, right? So here you can also take the less than condition. Then no need to connect the this gain. Okay, why? Because when these two are turned on, these two must turn off, right? When these two are turned on, these two are must turn off. That's why I am taking the -1 as gain. Why? Because this is the high, output is low. When this is the on, these two are off. This is off, these two are on. You can also use the less than condition. If you use the less than condition, no need to take the gain. Okay, and giving it to the MOSFET these two switches. That's it. Okay, now again take the same thing to the below H bridge also. Okay, but here we need to take the different values. Here sine wave is same, it does not change, 0 to 1 only, 0 to 2 only. Why? Because here sine wave is the same for the these two carrier waves, but the repeating sequence must be changed. So take the here time value is changed for these two, 0 to 1 for red one and 0 to 1 for blue one also. Okay, but the output value is changed. Here for second wave the output value is what? 1 to 2, right? Only. That's why I am taking the repeating sequence output values is 1 to 2. That's it. Now click on OK and give it to the MOSFET 4 and then this one. Okay, why? Because we need to turn on the these two at a time, and this to the this one and this one, like this. Here you can also change this one also, 0 to 1, and then here for second level you can get the 1 to 2. That's it. This is the connection of 5 level multi-level inverter. So now turn your circuit. Now open your scope. You can get the 5 level inverter output. These are the 5 levels, right? So here we are taking the input as 100 plus 100, means we are taking the 200 volts as input. Then you can get the output as 200, right? Here you can get the 200. For first level you can zoom it. If you don't see, unable to see, just zoom this one. Okay, these are the 5 levels where we are getting the 0 at the first level and 100 at the second level, 200 at the third level, and again minus 100 at the fourth level, minus 200 at the fifth level. These are the 5 levels we are getting. Okay, this is the 5 level inverter. And if you want to design the 9 level inverter, just take the another H bridge below and connect the cascaded like this. Okay, these are the 3 H bridges we are taking. Just only one change. In 5 level we are taking the 2 H bridges, but in 7 level we are taking the 3 H bridges. That is the only one change. Okay, here our connections are same, but the thing is you need to change the this sine wave amplitude and this repeating sequence, nothing but the carrier wave amplitudes. Why? Because this pulse width evaluation is only for what? Only for 5 level, right? For 7 level you need to take the another repeating sequence, right? Okay, so if you take the another repeating sequence, time is does not change, 0 to 1 only, but the amplitude is changed, 0 to 1 for this, 1 to 2 for this red one, 2 to 3 for this blue one. So here amplitude is 3. For first level you can take the only 0 to 1 as repeating sequence, and 1 to 2 is second bit, 2 to 3 is third bit. That is the only changes needed. Okay, so now open your MATLAB and take the sine value is 3. Okay, here I am taking the 3, right? So for first H bit we need to take the 0 to 1. So that's why I am taking the repeating sequence is 0 to 1 output value, and time value does not change for anything. Okay, so here I am taking 0 to 1. For second H bridges I need to take the 1 to 2, right? That's why I am taking the 1 to 2 is output value. Here also I am taking the 1 to 2. For third H bridges I need to take the 2 to 3, right? That's why I am taking the 2 to 3 here. So if you double click this one, I am taking the 2 to 3, right? Like this. Here also I am taking the 2 to 3 values. Why? Because here I am taking the 7 level inverter. Now run your circuit. Then you can get the 7 level inverter. These are the 7 level. If you are unable to see this one, just zoom this one. Okay, these are the 7 level. Here I am taking the, so here 3 bridges, right? Each bridge I am taking the 100 volts. Then you can get the 300 volts as the output. Here for first level 300 volts, second level 200, 100, 0, minus 100, minus 200, minus 300. Like this you can get the 7 levels. Okay, and if you want to design the 9 level inverter, take the another bridge. Then you can get the 4 bridges. Okay, so now design the 9 level inverter. This is the 9 level inverter, right? So here I am taking the 4 bridges, 1, 2, 3, 4. Here connections are also same, but the thing is to change is sine value is 0 to 4, because I am further increasing the another one. So here this is the 7 level. For 9 level you need to take the another carrier wave. Here time value does not change, but the amplitude is changed to 0 to 1, 1 to 2, 2 to 3, 3 to 4. Here final sine amplitude is 4. So that's why I am taking the sine amplitude is 4 here. Okay, all frequency and all thing is same. Okay, here for first bit always take 0 to 1. For second bit always take 1 to 2 output value. Time value does not change. For third one you can take the 2 to 3. For fourth bit you can take the 3 to 4. That's it. So now you can run the circuit and you can able to see the output by clicking the scope. Okay, now you can zoom this one, then you can get the 9 levels. So here you are taking the 4 bridges, means 400 volts. So this is the 400, 300, 200, 100, 0. Again 4, minus 100, minus 200, minus 300. So like this you can get the 9 level. For 11 level what we need to connect? You need to connect the another H bridge. So here total 5 H bridges you need to take. Now let's connect the 11 level. This is the 11 level inverter. Here you need to take the 5 H bridges, right? So that's why I'm taking the 1, 2, 3, 4, 5 H bridges. But the change is only you need to take the another carrier, right? So here amplitude is further increasing, 0 to 5 I want to take. Okay, that's why I'm taking the, for 11 inverter I'm taking the 0 to 5. So that's why I'm taking the amplitude is 5. For first H bridges you can take the repeating sequence 0 to 1. Second H is 1 to 2. Third H bridges 2 to 3. Fourth one 3 to 4. But fifth one you need to take the 4 to 5. Okay, that's why I'm taking the output value is 4 to 5. But time value does not change because here x-axis is change, x-axis is same, but only y-axis is changing. That's why I'm taking the 4 to 5 for 5th H bridge. Now run your circuit, open scope for to see the waveforms. So now zoom this one. These are the 11 levels we are getting. Here I am taking the 5 H bridges, means 500 volts. That's why I am getting the 500 volts here. Positive 500, 400, 300, 200, 0, minus 100, minus 200, minus 300, minus 400, minus 500. Like this you are getting the 11 levels. Okay. These are the connection of 5, 7, 9 and 11 level cascaded H bridge multi-level inverters. If you compare these two, if you increase the level, then you are getting the less number of harmonics. Okay. If you see the total harmonic distortion of 5 level inverter, now do FFT analysis for 5 level inverter, then you can get the THD. Okay. Total harmonic distortion of this one is 24.40, right? So this is the total harmonic distortion of 5 level. Okay. If you further increase the 2 levels, means if you go to the 7 level inverter, again you need to run and do FFT analysis, then you can get the THD as 16.64. Here in 5 level we are getting the 24%, but in 7 level we are getting only 16%. Means here harmonics is reducing, means quality of waveform is increasing. That is the difference between normal level and multi-level inverters. Okay. So if you further increasing the level, now you can open the 9 level, then run the circuit. What will happen? Let's see. Now again do FFT analysis. Here you can get the only 12% of harmonics. Okay. When compared to 7 level, here in 7 level we are getting the 16%, but in 9 level we are getting the 12%. Here harmonics is further reducing. And if you take the 11 level, and do FFT analysis, click on display, then here you can get the only 10% of the harmonics. Means here when compared to 5 level, 7 level, 9 level, this level inverter you can get the much lesser THD value. Okay, that is the use of increasing the level of the inverter. Okay.